Today is the final part of a three-part series called The Road to Validation. And what this is about is how we can use all of our tools in the design environment to do early stage validation through late stage qualification and replacement of physical testing. Last week we heard from Silvio Perez about the usage of the structural analysis tool SOLIDWORKS simulation, and in week one we heard from Damon Tardini about the SOLIDWORKS flow tool. The purpose of the series is to showcase a specific application through some of our design validation tools. In this case, we took a look at a fueling nozzle that we want to show there are options to vet different initial designs and early design qualification, including use of flow to tweak the nozzle throughput and use of SOLIDWORKS simulation to import some of those stresses, up to and including the replacement of destructing testing that we may do on these with expert level tool SIMULIA Abaqus. So once we looked at the flow characteristics based on shape, and we took a look at how we can assess thermal stresses and cyclic fatigue in SOLIDWORKS simulation. In this next step, we want to go up to looking at bolt preloads, solving for some complex contact, and going through a couple scenarios that induce quite a bit of plasticity and where we can get a look at whether or not our gasket stays fully in compression and whether we think we still have a good seal. So this next one will be a bit of a step up in terms of the complexity on the structural side. If you're talking about the software validation and predicting real-world design responses, we're talking about the simulation family of products among our offerings. We have solutions for data and revision management in the PDM, and we have electrical solutions and 3D print and computer-aided manufacturing solutions. But today we're really going to zoom in on the simulation side of our offerings. And if we look at the overall family of simulation tools, we specialize in quite a few different areas in the SOLIDWORKS realm. But today we're going to zoom in just in the SIMULIA Abaqus line. The offerings for simulation we have at Hawk Ridge vary from some basic simulation tutorials on our YouTube channel to technical support from degreed support engineers through a variety of in-classroom and online training. We do offer some flight plans to help you get your software configured and get you going on your first project. And we offer turnkey consulting where you can work with us to scope and execute projects on your company's behalf. If we look at the overall matrix of the SOLIDWORKS simulation package, you can see that you increase functionality and the complexity of the types of analyses that you can do as you work up the product line. The same is true if you look at where the SIMULIA Abaqus line fits in our offerings. Today I'm going to focus on, from the SIMULIA line, just on the Abaqus FEA tool, but I will touch a little bit on what you can get at with some of the other pieces of the tool here. So beyond Abaqus, we have some tools called EyeSight, FESafe, and Tosca. The keys to take away here is if you look in the top left, that's where the tool Tosca would come in. It's topology optimization. And what that is it's a non-parametric optimization tool that allows you to reshape your part based on finite element stiffness and mass. So it's a way that you can either optimize stiffness to weight, or you can optimize the external shape so that you reshape and get rid of hotspot stresses. EyeSight, excuse me, FESafe is a fatigue life tool that's strain-based fatigue. And so what that means is that your fatigue life isn't just based on picking the min and max stress and calculating a reversing load. You can track the strain throughout a loading history. So in this case, you consider the order that the part is loaded, whether you may have some low cycle event that induces some compressive stress that actually helps you on your cyclic fatigue, and you get a very detailed look at the fatigue life. Abaqus, of course, is used on the strength and stiffness side, and as well as being able to simulate certain manufacturing processes. And then with all of these tools, anything that you can parameterize, you can wrap iSight around, which is a process automation tool. And what that allows you to do is get some statistical probabilistic data about how different geometry or material property or loading characterization is going to affect your life prediction for your tool. So coming back to where we are in the series, in stage 1, we did SOLIDWORKS flow simulation, so fluid, flow, and thermal analysis based on a transient flow. In stage 2, we did some thermal stress and fatigue calculations. And in stage 3, we are focusing on a structural analysis with the SIMULIA Abaqus code. So you can see across the bottom, on the left, we have our flow simulation results. In the middle, we have our structural results based on that. And on the right, we have the Abaqus results showing a bit of shearing action at the bolts and at the interface of the gasket and the neck and the nozzle. So this is the third part of both the third part of the series and the third part of the analysis, where the bolts were first pre-tightened and locked at a certain position, and then that shearing load was applied. The reasons that we wanted to use Abaqus for this class of a problem is that it's key that we can sequence the steps of the analysis. So the first step is the bolt preload, and then the second is locking the bolt at that strain to do the additional calculations. Another part of that is that we can use the bolt preload solution to seed our other load cases. So we can use restart simulations to not fully solve retightening the bolts and applying the other loads. So both of the simulations you see on the right side of the screen, the moment load and the shear load, were based on the first initial bolt preload solution. So quickly going through what it takes to set up a problem like this, what I want to do today is show you the workflow to import the CAD and analyze this problem in CAE. The first thing to do is import some geometry, and that's going to be the nozzle, the gasket, and the neck. We're going to be running static analyses, so our study type, material properties, so we'll map some metal material properties to this. And you'll notice that over on the right, this is actually the drop-down menu from the software, and that these correlate to the steps over on the left that I'm walking you through. So when we get in the interface, that will make some more sense. But we'll map material properties, mesh, and all the analysis setup to it. So now I'm ready to start showing you the import and the setup of this in Abaqus. So first thing I'm going to do is use the SOLIDWORKS associative interface to export the geometry over to Abaqus. You can see that once we've imported that to Abaqus, we have a model tree over at the left. So we have the parts at the top left. We have the assembly where those parts are listed. And if we go down through the tree, all the things like contact interaction pairs are there. I'm going to use a tool called the Bolt Studio, and what this is an add-in where we can add a nut and a bolt of a particular configuration. So I'm going to tweak the default length a little bit for the bolt and enter that we want to, we'll change the length of the overall bolt and the thread, and I'll come in and place these on the surface that we want and the edge that we want to use for that. So now that I've made all the selections for the bolt face and the surface, we've inserted our bolt and nut. These are meshed, so one of the nice things about this is you don't spend a lot of time worrying about how the bolt or nut is modeled or meshed. It's just done. We chose the preload, so the bolt has 1,000 Newton preload, and what it does is cut a slice through a section of the bolt and apply that load. So we'll come down to the load module, and I can show you that. We choose one of the bolts and we look, there's 1,000 Newton amplitude through the middle. So that's the basics of setting up the bolted preload selection in assembly. that by default creates a couple steps. And once we have those steps created, I can come in and create a boundary condition on the assembly. So I'm going to go ahead and choose the bottom of it. I'm going to name the surface that I apply that to for later reference, and I'll just apply constrain it in all 3 degrees of freedom. So this is the basic setup of our bolted assembly. I'm going to zoom in real quick here on the bolt and just show you the type of mesh. You know, we have a capability to use hex elements with that, and coming back to the assembly, we can visualize the mesh of the full assembly. I'm going to go ahead and turn my color back to white. So, and we can turn off those axes, the bolt axes. They can cloud our view a little bit of what's going on with the assembly. So I'm going to go ahead and just turn off all the datums for this. And you can see I used a pretty fine hex mesh on the bolt, sort of default coarse mesh on the rest of the nozzle. And once I have everything meshed and the load set up, I mentioned that we have the capability to go through a few different step types. What those were is an initial bolt load step, one where we lock the bolts at length, and one where we load the nozzles. So going down to see how those loads are visualized, we can switch modules of the software here just to the where my mouse is highlighting, and so from within that we can also pick a particular load step to zoom in on. So I'm going to look at the nozzle load step. This particular step is the shear load at the end of the nozzle. We also have one where I've induced a moment load. So then the symbol is moment rather than bolt load, moment rather than shear load. But with that, the next thing to do is come to the job manager part of the software. And here, I've already run these, but this is where we queue up a job based on a particular model and we solve it. These took about a half an hour to run, so I ran them ahead of time. And I'm going to just go ahead and skip into the results. The results visualization has all the same sort of capabilities to slice sections. So I'm going to go ahead and cut a section on the Z plane. And with that, we're going to visualize the stress time history as this is preloaded and loaded up with a shear load. So in this first step, you can see the bolt load start to tighten. And once that is done, we are going to step through the time history of the nozzle loading. It's a pretty extreme shear load. This happened to be no friction set up in the contact condition for the gasket, so it's not really bearing any of the load. So as you'd expect, all the load of that assembly goes into the shear of those bolts. The other analysis that I ran was to take a look at what a moment load does. It's not going to be as extreme of action, and this one started with a restart analysis from the bolts already being tightened. So what you're going to see here is just the stress time history as the moment is applied. So you'll notice that the top bolt is relieved of some of the tension and the bottom bolt goes into a higher amount of tension. If we want to visualize what the displacement looks like, sort of as you'd expect, as you twist the nozzle at the end, that's the piece with the highest displacement. And if we map those by direction, of course, most of it is vertical because it's a pure moment load at the tip of that nozzle. We can do things like track plasticity, probably what you'd expect looking at this shear loaded nozzle is if we cut a section through it, that we have some pretty significant plastic strains on the bolts. You may have mentioned that you may have noticed that those bolts were sort of necked down. I chose one, I believe, from an automotive application where it's got a significant thinner spot, potentially a bolt that's torqued to yield. So we have some visualization options for, whether we show the mesh we can get a kind of a cleaner view of that if we turn off mesh visualization. So I'm going to go ahead and animate without, so we get kind of more contrast where we have some of these overstressed areas in the bolts. And that's really the highlights of going through setting up the loading process. You know, one of the things that we have the capability of doing is we can pick a spot to track a time history. So if we're, you know, we have a stress criteria that we're going to track through, you know, through the middle of one of these walls, we can pick a nodal result and pick a node. And we can map some stresses to that. So this can be used in a variety of ways. They can be filtered. You know, no real surprise, the stress is very low until we increment that ratcheting load up. But this allows you to do some numerical processing on this and go beyond just looking at a contour plot shape. So one last thing I want to touch on is the setup of the contact. What I used here is called general contact, and what that means is that the whole model basically searches for contact pairs everywhere between any part and itself or between any two parts in the assembly. This is a very powerful way to handle things like we know the bolts will preload, and then the shifting shear load is going to put those bolts in contact with the through holes on the neck and the nozzle. We don't have to anticipate where all those changes are, and it's a very stable scheme to sort of walk through all of that automatically. And you know, with that, I'm through all the analysis, setup, and processing of this part 3 of the road to validation. And I'd like to open it up for any questions at this time. Let's see. I'll go to the question section, but yeah, definitely chime in at this time with any questions, and love to hear your thoughts on this. I see one question asking about runtimes in comparison to SOLIDWORKS Premium. It's tough to do an apples-to-apples comparison, but for this class of contact problems, you have a lot of controls for things like panel T stiffness and your increments that your solver takes that make it possible to tackle problems that I believe you couldn't in any other expert level software. If we're talking about a small modal analysis, you are unlikely to see any real differences in solve time, but as you step up to very large model sizes, I think the limitation of the size of the model that you can handle is sort of removed, and you will find that for problems with a lot of nonlinearity, where they are possible in both software, they are going to be better addressed in Abaqus. So I'm not really seeing too many more questions at this time. So I'd like to thank you for attending today's webinar and invite you to reach out to me with any additional questions at timm@hawkridgesys.com.